Part 1 of this FRQ is to find the area of this region R. So we want to find this whole area here. Okay, so the first thing that we're going to do is we're going to want to find the endpoints of the area so we know where we're going to do our integral from. Luckily this one's pretty easy, and we know that one of our endpoints is going to be 1 here and one of our endpoints is going to be 0. So we already know that it's going to be the integral from 0 to 1. Find this area. We want to know the distance measured by dx, right? So in order to find the area of each little tiny sliver, we need to know the height of that sliver and then the change in x. If we were going to do this as a Riemann sum, you would have the height of each rectangle and then the change in x for each rectangle. But in this case, we're not going to do a Riemann sum, so we're going to need to know the whole height, and we're going to need to know delta x, but that's just represented by dx in our integrand. So in order to find this whole distance, we need to know the area under this curve and the area under this curve. So we're going to find this area and subtract this area from it. Now, it looks like you should add the two areas. However, since this area is underneath the x-axis, it would be negative area, and you would end up with a shorter height than is actually the height. So in order to correct for that, we have to subtract this area from this area. And since this line on top is y equals x e to the x squared, and this one on the bottom is y equals negative 2x, that is how we're going to do it. So I'm going to have the integral from 0 to 1, and I'm going to have my top function, x e to the x squared, minus my bottom function, which is going to be negative 2x. And then delta x, which represents the base of each tiny, tiny rectangle. So next what I'm going to do is I'm going to have to integrate this by hand because this is a non-calculator problem. So to make this easier for myself, I can split them into two different integrals, and that's what I'm going to do. I'm going to say this equals the integral from 0 to 1 of x e to the x squared dx plus, because those two negatives cancel each other out and become a plus, the integral from 0 to 1 of 2x dx. So for this, to solve this, I'm going to have to use u substitution. And the u that I'm going to use is going to be x squared, because I can see that the derivative of x squared, which would be 2x, but in this case we just want to be able to cancel out this x, is going to be there, so that's going to become my u. My du will be 2x dx, and so dx will be 1 over 2x du. And that means that this whole thing is going to equal, so the antiderivative of this is going to be really easy, e to the u over 2, because as we know, all integrals and derivatives of e to the x are just e to the x, and that's going to be evaluated from 0 to 1. And then the integral of 2x is going to be x squared, also evaluated from 0 to 1. And now I have to replace that u with what I substituted out earlier, which was the x squared. So now I have e to the x squared over 2 plus x squared evaluated from 0 to 1, which is going to give me so e to the 1 is just going to be e over 2 plus 1, right? Minus, because it's from 0 to 1, so I have to subtract at 0. E to the 0 is going to end up being 1, so it's going to be 1/2 plus 0. And e over 2 plus 1 minus 1/2 is going to equal e over 2 minus 1/2. And that will be the area of R. For the next part of this FRQ, we want to find an integral expression that will give the volume of the solid generated when R, this area, is rotated around the line y equals -2, which I've drawn here. So it's kind of weird to conceptualize these problems because, you're given this 2D area and you have to think about it in a 3D manner. However, what we really just need to think about is the cross sections and finding the area of the cross section, because dx will just give us that other area in our integral. And so again, we already have our endpoints really easy, 0 and 1, and so we can write that out right away. Perfect. So we're rotating this solid here around this line. So it's going to be rotated like this, perpendicular to the x-axis. And what our cross sections are going to end up looking like washers, right? Except for one at the very end, because you have this area and then there's some empty space. So they're going to end up looking like this, like a washer. And so in order to find the area of this washer, we would find the area of this circle and then subtract it from the area of this larger circle. And that's exactly what we're going to do to find the volume of this area by finding each cross section's area and multiplying it by delta x. So in order to find the area of the big washer, it's going to have this radius r, right? Whereas the small washer will have this radius, and we'll call that lowercase r. And we know that the area of a circle is pi r squared, right? So we want to find the area of this washer, the area between these two circles. We're going to have to subtract this area from this area. And we know that the big R, because it's the furthest one away from the line that we're rotating it around, is going to be y equals x e to the x squared. So big R is going to be x e to the x squared. And that means that our little r is going to be -2x. So in order to put this in our integral, we know that we're going to have to factor out a pi, and so we'll just put a pi right out front of the integral. And then we know we're going to end up subtracting these two areas. So we're going to subtract this area from this area to find out what this in the middle radius will be. And then, since the area of a circle is pi r squared, we have to square this whole area, and then we'll write dx. And just for cleanliness, I'm going to rewrite it. So the expression will be pi times the integral from 0 to 1 of the quantity x e to the x squared plus 2x squared dx. And that delta x is what's going to turn this area into a volume because it gives it the next the change in x for each cross-section. Third part of this FRQ, and the final part of this FRQ, we want to find an expression that gives the perimeter of R, which is this area. So in order to do that, we're going to have to find this, the length of this, the length of this, and the length of this. So let's start with the easiest one. Easiest one is going to be to find this length, right? The distance of this is really easy to find because it's at the same x value. So we just need to subtract the y's. So it's going to be e minus -2, which is just going to be e plus 2. Now for the other two, we're going to have, for this one, we can use distance formula. And the distance formula is the square root of x sub 2 minus x sub 1, quantity squared, plus y sub 2 minus y sub 1, quantity squared. Now we know this point is 0, 0, and this point is 1, -2, so we can easily find this. Our second x is going to be 1 minus 0, that's just going to be 1 squared, plus -2 minus 0, that's going to be -2 squared. This is going to be square root of 5. So now we have this distance and we have this distance, but we need to find this distance. And this one is going to take something called arc length. And the formula for arc length looks like this, and then I'll explain why. The integral from a to b of the square root of 1 plus f prime of x quantity squared dx. Now if you look at this formula, the square root is very reminiscent of this formula here. And we know that f prime of x represents the slope, and since slope at any given since slope for a line can be represented as y sub 2 minus y sub 1 over x sub 2 minus x sub 1, you can see that in the distance formula, and that pretty much gives the formula for arc length. So in order to find the arc length of this, we first need to find what y prime is. And for that, we're going to have to use product rule, right? So first we're going to do the derivative of x, which is just 1, times e to the x squared. And then we're going to add x times the derivative of e to the x squared, which, because we'll have to use chain rule, is going to be 2x e to the x squared, which means y prime is going to be e to the x squared plus 2x squared e to the x squared. And if we wanted to simplify this, we could say y prime equals e to the x squared times 1 plus 2x squared. And we know that our endpoints are going to be from 0 to 1. Of the square root of 1 plus quantity e to the x squared times 1 plus 2x squared squared dx. And that's going to give us this length. But we can't just leave these all separate and have that be our answer. Sorry, let me adjust this. There we go. We have to combine them all together to show perimeter equals e plus 2 plus the square root of 5 plus the integral from 0 to 1 of the square root of 1 plus quantity e to the x squared times 1 plus 2x squared dx. And that's the end of the FRQ. Thanks for watching, and I hope it helped.